This is video 1A for the Year 12 Mathematical Methods course. In this video, we're going to cover the theory behind first principles under the topic of differential calculus. Specifically, we're going to explore why differential calculus is so important, average rates of change, instantaneous rates of change, the derivation of the limit formula for derivative functions, techniques involved in finding the derivative of different functions using first principles, and then we're going to cover some example questions. First principles in the world of calculus is quite an interesting chapter. The main reason for that is it really shows where the origins of calculus were, and more so emphasizes how far we've come in using different techniques and different rules for figuring out the exact same thing. Now, in this video, we're going to be covering a bit of revision from the first principles chapter that you would have covered in year 11, and then we're going to show how this chapter expands into the year 12 course. So let's do a little bit of revision from our year 11 course first. First things first, calculus in itself is the study of how things change. So whether that be motion or business trends or financial purposes, it's a very, very practical application in the modern world, because whether you are an athlete or you're a businessman or you're an accountant, you are constantly looking at how the world around us is changing and how that can help us to predict patterns in the future. So it's a very, very good topic to really get your head around. In a more mathematical sense, we look at how graphs change. So let's say we've got this function here. Nice, simple curve. So then the study of calculus could be something along the lines of, I have this particular point here. Let's call this point at point A. And I want to figure out how quickly the graph is changing at that particular point. Now, if you recall from last year, you've got two different ways that you can look at this. The first way is that you can approximate using an average rate of change. And the way that we use an average rate of change is we would choose a secondary point. Let's use this green point here. We would draw a line segment between these 2 points, which is called a chord. And then we would figure out the derivative or the gradient of the slope between these 2 points. So you would choose a secondary point, and then you would find the gradient of the chord connecting the points. But once again, this, while it is a very simple and convenient technique, it is only good for approximating the rate of change at the point that we're concerned about. Let's think about why this might be. As a secondary bit of revision, what you need to remember is that when we're talking about the rate of change at a particular point, we use the phrase the instantaneous rate of change. So that's a very, very important term there. And the way that we graphically represent the instantaneous rate of change at a particular point is we draw the tangent to the curve at that particular point. So that would be something along the lines of that tangent there. And then we need to figure out the gradient of that tangent. So let's just write this down here. The true, or most accurate, rate of change is the instantaneous rate of change. And this here we can find by calculating the gradient of the tangent at the point of interest. Coming back to our discussion then of average rates of changes and the approximation, if we have a look at the chord that we just drew and then the tangent that we drew there, we can see that whilst the two lines are relatively similar in terms of their steepness, they're still not the exact same. So what we can do to create a better approximation is we can choose a secondary point which is even closer to the point of interest. Because then if we draw this chord, then we can see that that chord there and the true tangent are a lot more similar in terms of their steepness. And what you can probably guess is that as the secondary point gets closer and closer and closer to the point of interest, then our approximation becomes more accurate. So that's a very, very important idea here. So let's write that here. As the secondary point gets closer to the point of interest, the average rate of change becomes more accurate to the instantaneous rate of change. Perfect. Alrighty, now that we've got all that technical stuff behind, let's talk about a little bit of notation. So let's say we have a function f of x. Then if we want to figure out the instantaneous rate of change at a particular point, then if this here is the regular function, then we have what is called the derivative function. And if we just use an example, let's say we had the point at x equals a, then what f dash of a would represent is, well, we can actually explain this in two different ways. The first way that we can explain it is that this would be the instantaneous rate of change of f of x at x equals a. Or the other way that you can think about this is that this is the gradient of the tangent to f of x at x equals a. So once again, either one of these two interpretations is absolutely correct. My suggestion is to get your understanding behind both of these because they both have very different types of questions that you could be asked in both tests and exams. But overall, it's just good to be able to interpret this one thing here in the two different ways that you're talking about. Now, just for a little bit of extra notational stuff, if you actually start off with a function, let's call it y, then you've got two different ways that you can represent the derivative function in this case. So if y is your function, then you can either write it as y dash, or we can write something called dy by dx. And these two here are what are called your derivative functions. There is absolutely no difference between these two forms of notation here. It just depends on what you're being asked for in a question. Furthermore, which one you just prefer. But either one is absolutely fine in most different scenarios. Now, let's talk about limits for a little bit, because this is our last bit of revision before we actually get into the crux of first principles, but it is still quite an important thing. The whole idea of a limit in mathematics is that we may have a function and we want to get very, very close to a particular x value. And we want to then figure out what happens to the actual function as we get closer and closer and closer. So let's start off with a nice simple example. Let's say we've got the function y equals x squared. And I said to you, I want to discuss the limit as x approaches 2. So what happens when the graph gets closer and closer and closer to that x equals 2 mark? The notation that we can write behind this is the limit of x squared as x approaches 2. Now in this particular case here, if you use your graph or just a little bit of common sense, then we can see that as x approaches 2, then the function is going to approach 4. The reason why we can very easily calculate that is because 2 squared is 4. So that's just a simple substitution. It becomes quite important when you have situations such as this, when you might have the graph of 1 over x, for example. Because what would happen if I then said to you, I want to discuss the limit of x approaching 0 for 1 over x. Well, what we can see here is that the x equals 0 point is an asymptote of the particular graph, so that there is going to be undefined. So this is the big blockage of limits in calculus, because in some situations we're going to be dividing by 0, which is the ultimate one rule of maths that you can never ever do. However, when we tackle the more first principles based questions, we'll see that we have ways of getting around that. But just something to think about for now. Okay. Now that we've talked about limits, that pretty much concludes the revision portion of this particular video. So now let's actually get into the crux behind first principles. So what I want to do is I want to revisit that graph that we had before, where we've got a nice simple curve that goes up something like that. And let's say I've got this particular point here. Let's call this at point A. And I want to figure out the derivative at that point there. So once again, let's say this function here is f of x. So my big question then is, what is the value of f dash of a? Because that then represents the instantaneous rate of change at that particular point. So once again, using this whole idea of an average rate of change, I can just choose a secondary point, connecting those two there with a straight line, and then figure out the gradient of that straight line. And once again, the closer these 2 points get to each other, the better that approximation is going to be. So I could even do something like that, or I could borderline have them right next to each other, and then the approximation is going to become even better. So the way that I want to do this is I'm going to just slightly redraw this diagram to make it look a little bit nicer. But let's say I've got this particular point here at a point x. And I'm now going to choose a secondary point, let's call it this point here. And this point here is going to be a distance of h away from my point of interest. So then the x coordinate of this point is going to be x plus h. Again, this is just very general terms. So then the chord between these 2 points could look something like that. Now the other thing I want to do is figure out what the y values of these 2 particular points are. So because we've just got the function as f of x, then the y point for that point there is just going to be f of x, and then the one for this secondary point will be f of x plus h. Now we just said before that to calculate the average rate of change, so I'll just say average rate of change, is going to be the gradient between these 2 points here. Well, in this case here, the difference in the y coordinates will be f of x plus h minus f of x, and then the difference in the x coordinates will be this x plus h minus the x. If I simplify the denominator just a little bit, it's f of x plus h minus f of x divided by x plus h minus x, so that'll just be h. So that there is a very nice standard form for the chord gradient between these 2 points. However, we said before that an average rate of change is good, but it's not great. So the way that we get to a more accurate answer is we need to close in the gap between these 2 points here. Now, if we think about this in terms of just a very graphical sense, if we close in the gap between these 2 points, it means that this value of h is going to get smaller and smaller and smaller. In fact, the smaller the value of h, then the more accurate our approximation is going to be to the true value of f dash of x, which is exactly what we're trying to figure out. So what we can do here is we can say then that f dash of x is going to be the limit as h approaches 0, or in other words, as h gets smaller and smaller and smaller, of this equation up here, which was the gradient function. And this here should hopefully ring a little bit of memory bells from your year 11 studies. This here is the derivative form first principles, which is a very important equation to remember. But once again, this whole idea of a limit is quite important because, again, we're saying that the approximation gets better and better as this value of h gets smaller and smaller and smaller, because then the 2 points are a lot more close together. However, if we come back to our discussion of limits again, we have one big problem with this equation. If we substituted in h equals 0, then we're dividing a fraction by 0, which again is the one cardinal rule of mathematics that you can never ever do. So when we tackle these different types of problems, we need to find a way to eliminate the problem of dividing by 0, because that's the ultimate rule that we need to try and get around in these particular cases. Now, in your Year 12 studies, we're going to be tackling 3 different kinds of first principles questions. The first one is where you just have a polynomial. So for example, you could have x squared, or 3x power 4, or half x power 3. But anything where you just have, a constant and then x to the power of something, you could have, like plus 3 in the ends of these. But you've got your quadratics, your cubics, your quartics. You could even have a linear graph in there at some point. These ones here are relatively nice to get around. But then the more complicated ones are where you have reciprocal functions. So examples of this could be 1 over x, or 1 over x squared, or 1 over 2x plus 1. So where functions where you have x's on the bottom of a fraction can be relatively difficult to work around. And then the third one are radical functions. Or in other words, where you have the square root of x, or the square root of x squared plus 5, or the square root of x plus 3, or something along the lines of that. Now, the thing is, when you're tackling these 3 different scenarios, you always have to use a very different rule to tackle each. And what we're going to be going through in this video is an example of how you would tackle each one of these 3. And then I would highly suggest looking at the application video for this chapter for a more detailed discussion of going through different examples. Because the thing about the First Principles chapter in Year 12 is that you go through this chapter at the very, very start of your discussion of calculus, and then you never really touch it again, because you've got all these extra rules that you would have touched on in Year 11 that makes finding the derivative functions significantly easier. In your exam, I can guarantee that you'll receive at least 1 question on first principles, and typically these questions are worth about 5 or 6 marks. So it's very, very beneficial for you to understand how to tackle any types of these questions, because then it's a very easy way to get about 5 or 6 marks in your final exam. And once you've done enough of these types of questions, usually they'll all turn out to be relatively easy, because it's more so about understanding the techniques and then just applying it to the different functions that you may have to work with. And this is where practice is definitely going to make perfect. Alright, so as promised, let's go through one example from each of these, and we'll discuss some good techniques on how to tackle them. So as a first example, let's look at the standard polynomials. So as an example, I want to figure out the derivative function of f of x equals x squared. I'm going to make a very big point about the way that you need to lay out these answers at every single example, mainly because when you're dealing with these questions, they're typically worth about 5 or 6 marks, as I said before, and the way that they can very easily deduct marks from you is by incorrect notation, which is a very, very easy thing to get right if you understand what you're doing. So the way that you always need to start off these questions is with the standard first principles derivative formula. So that's f dash of x is the limit of h approaching 0 of f of x plus h minus f of x divided by h. Now, where a lot of kids usually go wrong here is they make an incorrect substitution into the formula above. So we know that f of x is x squared. So to figure out the function for f of x plus h, we need to see where we've got an x in the original function, and we replace that with an x plus h. The easiest way to make sure you do this right is by surrounding the x with a bracket and then just replacing that bracket with x plus h. So if I instead write this as bracket x bracket squared, then I can very easily see that f of x plus h will be x plus h all to the power of 2. Substituting both of these into the original formula, we get f dash of x is equal to the limit of h approaching 0 of x plus h squared minus x squared divided by h. Now, the big rule when you are working with first principles with standard polynomials, I'm going to write this here, is you need to expand any brackets and simplify. So pretty straightforward. Nothing that we haven't really seen or done before. So let's do that. So we've got the limit of h approaching 0. X plus h squared will get reduced down to x squared plus 2xh plus h squared. You can manually do that expansion if you would like to, but hopefully you should be able to do that off the top of your head at some point. And then we've just got the minus x squared as well, so remember to put that at the end, all divided by h. In this case here, I can see that the x squared and the minus x squared will cancel. So now we can write out what's left, which is the limit of h approaching 0 of 2xh plus h squared divided by h. Now, as a quick check when you're doing these types of questions, after you do the expansion and simplification, the number one thing you should have is an h attached to every single term on the top. And that's exactly what we've got here. So if for this first term, we've got a h here, and for this second term, of course, we have a h, because it's just h squared. If you have a term that does not have a h with it, then you need to go back and see where you've done something wrong, because it should always reduce down to terms that only have h's in them. Because what we can do now is we can factorize out a h from both of these top terms. So if we pull out the h, then we've got 2x plus h, all divided by h. Now, this is the great thing about these types of questions here. You know that you're on the right track if you now are able to cancel out the h from the top and the bottom. Because what we're going to be left with now is the limit of h approaches 0 of 2x plus h. Now, let's think about why this is a very, very good thing. The whole problem with first principles is that we cannot divide by 0. That is the one thing that we can never ever do in just any of mathematics. So what have we done here? We've actually cancelled out the h on the bottom, which means that if we now make the substitution of h being 0, let me just write this here, let h equal 0, then this here is going to turn into 2x plus 0, so we're not dividing by 0 anymore. So that's really, really good. So then this will just reduce down to 2x. So that means that f dash of x is equal to 2x. Now, one quick thing I want to make mention of is that you'll notice that in every single line throughout this entire question, I write out the limit part at the front. And that is because we are still having to acknowledge that at some point we need to let the h become very, very small. Or in other words, just let it equal to 0. The only time you do not write that limit is when you make the substitution of h being 0. So you'll notice that I haven't written it at this point here and neither at this point because we've already made that substitution of 0. Just a quick thing, if you do not write out the limit at every single line, then they will deduct a mark very, very easily from your test or exams, okay? Make sure you do that. It's such a simple thing, but just make sure you're doing it at every single step until you make that substitution. Okay, so that's that first example there. The polynomial ones, again, are relatively nice in that aspect there because the main thing you just need to do is to expand and simplify any brackets that you've got on top. Let's have a look now at doing a reciprocal function. So in this case, let's do f of x is equal to 1 over x. So once again, when you're dealing with first principles, first thing you want to do is f dash of x is equal to the limit of h approaches 0 of f of x plus h minus f of x, all divided by h. So once again, we start off with the function as 1 over x. So then the function of x plus h will be 1 over x plus h. So again, just replace the x with an x plus h. Substituting both of these into the original function, we get f of x is equal to the limit of h approaching 0 of 1 over x plus h minus 1 over x divided by h. Okay, so this is where things get a little bit more complicated because unlike the first example that we went through, we no longer have any brackets that we can expand and simplify. In fact, we've now got 3 individual fractions that we now have to take care of, which is quite annoying. However, The way that we get around this is as such. We multiply the top and the bottom of the overall fraction by the product of these two smaller denominator here. So in other words, I'm going to multiply the top and bottom by x plus h and x. So this is our number one rule when we're dealing with reciprocal functions. So I'm going to write this out here. Multiply the numerator and denominator by the product of the two smaller denominator. So once again, that's just this denominator here and this denominator here. Put them together and we're going to multiply the top and the bottom by that. Because let's see what happens when we expand out this. So we've got the limit of h approaches 0. If we look at the bottom, then this stuff here is just going to get attached to the h. So let's just write that as it is. H, x plus h, then x. Then on the top, we're going to have to make the distribution of this stuff here to this fraction and to this fraction. So let's write out that as it appears. So we're now going to have x plus h and then x divided by x plus h minus x plus h over times by x divided by x. So that's just by distributing this new numerator to the two individual fractions. Let's look at why we did that. If we look at this first fraction here, we've got x plus h here and we've got an x plus h there. So those two there can cancel. Then with this second fraction, we've got an x here and we've got an x here. So those two there can cancel. If we write out what's left, then we've got the limit of h approaching 0. Then we've just got x minus x plus h divided by h, x plus h, and x. Two things here I want to make mention of. The first thing is you'll notice that I haven't done anything with the denominator of this overall fraction yet. The main reason for that is because similar to our first example, our main goal is to try and get rid of that h, so it doesn't really make much sense to expand. The second thing I want to make mention of is that the reason why we did all that elaborate expansion is because now on the top, we no longer have fractions. And not having fractions is the one goal when you have this kind of first principles question. Because now the numerator is going to very easily reduce down to x minus h over h, x plus h, x. The x and the negative x will cancel. So now I'm just left with the limit of h approaching 0 of negative h over h, x plus h, then multiplied by x. Quick sanity check. As I mentioned before, when you get to this point here, you should only have terms on the top that have a h attached to it, which is exactly what we've got here. So that's really good. And now I can cancel out that h with that h. So what I'm now left with is the limit of h approaching 0 of negative 1 over x plus h multiplied by x. This is really, really good because once again, now that I've cancelled out that h on the denominator, I can now set the h as 0. So we can now say let h equal 0. So then this here is going to turn to negative 1 over x plus 0 multiplied by x. Once again, you'll notice I'm no longer writing the limit notation because we've already substituted in the h equals 0. This is then going to turn to negative 1 over x times by x, which is negative 1 over x squared. So that's f dash of x is negative 1 over x squared. So that's that one there. Now, the third and final type of question that you could get, the radical functions. And the example that we're going to look at here is f of x equals the square root of x. Same deal as the last two. First thing you want to do is try and identify your functions of f of x plus h and f of x. So in this case, f of x is still just the square root of x. So then f of x plus h will be the square root of x plus h. Writing out our standard form for f dash of x with the first principles notation, it's the limit of h approaching 0 of f of x plus h minus f of x divided by h. Putting in the two functions that we've got, that's the limit of h approaching 0, the square root of x plus h minus the square root of x divided by h. Alrighty, so unlike the last two, with polynomials we expanded and simplified. We don't have anything that we can expand and simplify here. With reciprocal functions, we multiplied by the denominators, but in this case here we don't have any fractions. So what do we do in this kind of scenario here? Well, we are going to multiply the numerator and the denominator by the radical conjugate of the top. Now, if you need a reminder about what a radical conjugate is, it would be something like this. The square root of x plus h plus the square root of x. So in this case here, I'm going to multiply by the exact same thing that we've got on the numerator, but I'm going to switch this minus out for a plus. Let's write a bit of a rule for this. Multiply the numerator and denominator by the radical conjugate. Okay, so let's have a look at what happens when we expand out this and multiply. So we've got the limit of h approaching 0, and I'm just going to write these in brackets for now just to make sure we don't mess anything up. So we've got all that stuff on the top, and then once again on the bottom, I'm just going to do it as h multiplied by all of that, just to make things a little bit easier to look at. Okay, so what we've got on the numerator here is we've got the square root of x plus h minus the square root of x, all multiplied by the square root of x plus h plus the square root of x. What I'm noticing this top part looks like is a difference of two squares. Because if you may recall, if you have two numbers, a and b, and you do a plus b, then a minus b, this very easily reduces down to a squared take b squared. So this is the difference of two squares. And this is exactly what we've got here, where that's a and b, and that's a and b. So what then the numerator is going to reduce down to is going to be the square root of x plus h all squared minus the square root of x all squared. And I hope you can kind of see where this is going to go. I'm just going to write the denominator as it appears, because I don't want to touch that just yet. If we look at then the first term on the numerator, we've got the square root of x plus h all squared. So that's just going to then turn to x plus h. And then the square root of x squared is just x. And that's really, really good because now the numerator is going to turn to x plus h minus x over h square root of x plus h plus root x. This x and that x are going to cancel. So then what we're going to be left with is the limit of h approaching 0 of h over h square root of x plus h plus the square root of x. These two h's are going to cancel. So then what you're going to be left with is the limit of h approaching 0 of 1 over the square root of x plus h plus the square root of x. Similar to our last two examples, now that we've eliminated the h on the bottom, we can now set h equal to 0, which we can write as then 1 over the square root of x plus 0 plus the square root of x, which is going to be 1 over root x plus root x, which is the exact same as 1 over 2 root x. And that there would then be our final answer. So those three, again, are the three different types of questions that you could be expected to work with when it comes to your summative tests and your final exam. So I'm going to highly suggest that you revise these three big rules and these three different approaches, because once again, if you understand how to use these three rules in any of the different cases that you may be presented with, then these questions are going to fall out to be quite nice. The hardest parts realistically are just the algebraic expansion and simplification, because of course one mistake will mean the rest of it will stuff up. But with enough practice, you'll get quite confident with a lot of these. If you do need a bit more practice, then I'm going to highly suggest you go to your textbook and essentially just try out as many different questions as you can. Furthermore, have a look at the corresponding application video to this theory video, where I will be going through quite a few different examples of exam questions based around first principles. Alrighty, let's wrap up. So in this video, we've delved into the world of differential calculus. We started by discussing how calculus is used to examine how the world changes. We then revised how we can use the gradient of the chord between 2 points on a curve to find an average rate of change. The limit formula for derivative functions was derived, finding that for a function f of x, the derivative function is f dash of x equals the limit of h approaching 0 of f of x plus h minus f of x, all divided by h. Finally, we explored the unique methods needed to find the derivative functions of polynomials, rational functions, and reciprocal functions using first principles, and applied these techniques to exam-style questions. And that's it for now. See you in the next video.